Okay, in this video, I will solve the practice final. I will start from the true-false questions. Question A, 1A, every interpretation fixes a domain. That is true. It is part of what an interpretation is to fix a domain, because an interpretation starts by fixing a domain and then it continues with assigning a reference to names and then extensions to the predicates. So it is true that an interpretation fixes a domain. Every first-order language can express the English quantifier. No, that's also true. It doesn't express it as a primitive symbol, but we said in class that there is a way of expressing no in terms of negation and exist. And also no can be expressed as for all and negation. The string for all x rxy is a grammatical sentence of first-order logic. That is false because this is a grammatical formula but not a grammatical sentence. The string for all x there is a y rxx is a grammatical sentence of FOL. That is true because even though this quantifier here is not binding any variable, there is no requirement in the definition of a sentence that there be no vacuous quantifiers or that every quantifier bind a variable. A sentence just is a formula that has no free variables. Every tautology, so in truth functional logic, is a valid sentence in first order logic. That is true because if there is no row of a truth table in which a sentence is false, then there is no interpretation in which that sentence is false. But the opposite of this is not true. There's going to be some valid sentences in first order logic that are invalid, that are not tautologies. Right, so this was our initial motivation for studying first order logic in the first place. And so, in fact, this F gets at this question. F says every valid argument in first order logic is valid in truth functional logic. This is false. There are some valid arguments in first order logic that are not valid in truth functional logic. For instance, the argument from for all x f of x to there is an x f of x that is not valid in truth functional logic because it is valid because of the meaning of the quantifiers. The main operator in this formula is the second universal quantifier, the one that binds y. This is false because the main operator is the first universal quantifier, the one that binds x. The rule of existential introduction requires a subproof. This is false because existential introduction is just the rule that tells you that if you have some formula f applied to some name c, then at a later line you can derive there is an x f of x. The rule of universal elimination requires a subproof. This is also false. Because universal elimination, remember, is the rule that tells you that you can go from for all x f of x to f of c for whatever constant c of your choice. All right, let's move on to problem 2. Formalize these sentences in FOL. And note that some might be true and some might be false. You're not trying to decide whether the sentences are true. You're just trying to decide how they're going to be expressed in FOL. The symbolization key is given on the next page. So we're going to refer to it as needed. But for now, I'm going to start with just this symbolization. So first, we're going to do every planet is closer to the sun than Pluto. It's actually useful here to go look at the vocabulary for this language. That's not what I meant to happen. So I'm gonna write here every planet is closer to the sun than Pluto. That's number one. The thing to remember here is that when you're formalizing with every, you always have to remember that you need to use a conditional, right? In almost every case, every planet, blah, 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 gets translated as a conditional, but when you translate with the raised and the existential quantifier, you typically want conjunction. The next sentence is, there is a planet that is warmer than Venus. Let's go back. So we're gonna use conjunction because we're gonna say there is an X is a planet, and X is warmer than Venus. 3, some planets are close to the sun than Earth, and some are not. I'm gonna think of this first by thinking of the Loglish form. We're gonna say there is an X is a planet, and X is closer to the sun than Earth. Conjunction, there is a Y is a planet, and Y is not closer to the sun than Earth. So here's how I'm gonna write this. I'm gonna say there is a X is a planet, and X is closer to the sun than Earth. Conjunction, there is a Y. It doesn't have to be Y, but let's keep it as transparent as possible. Y is a planet, and Y is not closer to the sun than Earth. 4, none of the planets is warmer than Pluto. So I'm gonna say it's not the case that there is a planet that is warmer than Pluto, such that X is warmer than Pluto. Earth is the coldest planet, and now I'm gonna give you a hint for how to think about this. So we're gonna have a predicate P for planet, then we're gonna have a predicate with 2 arguments, C, saying that the first argument is closer to the sun than the second argument. So here I'm not using a 3-place predicate of closer to X than Y. I'm using a 2-place predicate that just relates to objects. And then for Pluto, I'm gonna use P, and for, I think that's it for this sentence. Let's go back. Our vocabulary here, we have a 2-place predicate, W, for the first argument is warmer than the second argument, and we have a constant A for Venus. Earth is a planet, and every planet who is on Earth is warmer than Earth. So that's what I'm gonna translate. So first I'm gonna say Earth is a planet. Let's say Earth is a planet. And then I'm gonna say every planet. But I also here have to say planet that is not Earth. For every object that satisfies this property, then I put my conditional, is warmer than Earth. It is warmer than Earth. Six, Earth is the coldest planet. So I'm gonna say the same thing as I said before. I'm gonna say Earth is a planet, and it's the coldest planet. And something is colder than Earth. This is in fact a contradiction because we just said that Earth was coldest, but anyway. There is a Y such that Earth is warmer than Y. Okay. So that completes the formalization exercise. So next up is this problem 3 of finding an interpretation that makes true the formalized versions of all of the first 5 sentences in problem 2. So let me blow this up. Let me also just repeat that even though these sentences have 2 place predicates, in the one in the final, you are only going to have 1 place predicates. Okay, so we want to define an interpretation that makes all 5 of these sentences true. We're going to assume that we're going to have at least 3 objects. We're going to have Pluto. So there's going to be the interpretation of P is going to be the planet Pluto. The interpretation of A is going to be Venus. And the interpretation of E is going to be Earth. And we're actually not going to assume that there are any other objects. So we're going to assume that the domain is just these 3 objects. Pluto, Earth, and Venus. Because it's easy to keep the domain simple if you can. So let's look at the things that are absolutely forced in this interpretation. We have to define a few things. We have to define the interpretation of the predicate P, and we can do it with a table. So we're going to have a table that's going to say for each of Pluto, Earth, and Venus, whether they satisfy the predicate P. And then we're going to have to define interpretations for warmer. We're going to do it with the graphs. And then we're going to have to define an interpretation for closer. And we're also going to do this with the graph. So how do we go about this? First, we're going to notice the things that are forced, right? So in this example, we have to make Earth a planet. So that much is guaranteed. Next, another thing I notice when I look at sentence 3, I notice that there's going to have to be another planet in addition to Earth. Because this says that there is a planet that's colder than Earth, and there is a planet that is not colder than Earth. So whichever way we want to think about the extension of C, we can't have Earth be both of these planets, so there's going to be another planet. Let's just say that the other planet is going to be this. Okay. Now, let's work on making sure that sentence 1 is true. So sentence 1 says, it says everything in our domain is closer to the sun, than Pluto. C means closer to the sun. Okay, so we just go back to the interpretation now of closer to the sun. And we want to make sure that we put that Earth is closer to the sun than Pluto, and Venus is closer to the sun than Pluto. So that relation holds in that direction. Okay, the second sentence says that there is a planet that is warmer than Venus. So we go out here to the interpretation of warmer. We have Earth, Venus, and Pluto. We just want to make sure that some planet, maybe Earth, is going to be warmer than Venus. The fourth sentence says that nothing that is a planet, so no planet, is warmer than Pluto. This is true right now because, in fact, right now, nothing is warmer than Pluto. There is nothing that bears the relation of extra warmth to Pluto. There is no arrow that goes from anywhere in this diagram to Pluto. So that is true. And finally, the last sentence says Earth is a planet, which we have because we make sure to put a plus here. And for every other planet that is not Earth, that planet is warmer than Earth. So here, to make this true, we have to do something that violates our intuitive understanding of the predicate warmer, but remember, we are constructing our interpretation. We can make it be whatever we want. So in other words, to make this true, we have to make that warmer goes both ways between Earth and Venus. Okay, let me just go through every one of these 5 sentences and explain why our interpretation satisfies them. By the way, let's complete this interpretation by saying that Pluto is not a planet. Okay, sentence 1 says, every planet is closer to the sun than Pluto. So the planets in our interpretation are Earth and Venus, and each of them is closer to the sun than Pluto. So we got that. There is a planet that is warmer than Venus. We made it Earth. We didn't have to make it Earth. We could also have made Venus be warmer than Venus, because again, we don't have to respect the intuitive meaning of warmer in coming up with this interpretation. But in any case, Earth is warmer than Venus on this interpretation because there is an arrow connecting E to V. 3 says, there is a planet that is closer to the sun than Earth, and that is not true. Well, we can make this true by making Venus be closer to the sun than Earth. So we could say this. And there's a planet that is not closer to the sun than Earth. That could be Earth itself. Sentence 4 says, it's not the case, there is no planet that is warmer than Pluto. Indeed, that is true, because there is no planet that is connected by the doubly relationship to Pluto. And 5 finally says, Earth is a planet, for sure, Earth is a planet, and every planet that is not Earth is warmer than Earth. The only planet that is not Earth is Venus, and we drew an arrow from Venus to Earth to signify that it was warmer than Earth. Again, this is not a meaningful interpretation of warmer, because warmer would not allow you to go from E to V and backwards, but first order logic does not know about this kind of meaning constraint. All right. Now, the next problem is going to be the same, except you have to add one complication, which is that you also have to add this last sentence. And this last sentence is basically the conjunction of sentence 5, so I'm not going to repeat sentence 5, with this other bit, which is that something is warmer than Earth. So sentence 6 is a 5. Plus an extra conjunct, which says that there is something such that the Earth is warmer than it. Now, I'm not going to go through all the details here because we know that this is already true in this interpretation. This makes me think, by the way, that the interpretation that we came up with problem 3 is probably not the simplest interpretation that shows that all these sentences are consistent. And that this interpretation that we actually came up with has this stronger property of satisfying the sentence in problem 4 as well, namely sentence 6. Now let's move on to the next batch of problems. So these are the more standard kinds of problems concerning showing validity and invalidity. So let's start with 5. We want to reason about interpretation to show invalidity. So we just want to construct an interpretation that makes the premises true and the conclusion false. Here we have no names, so the interpretation boils down to choosing a domain, which I'm going to choose to have two objects, A and B, and interpreting the predicates P and Q. As I mentioned in class, in interpreting the predicates, we want to start with the forced choices. In particular, if EXPX is false, then these two have to both be minus, because if even one of them was plus, then EXPX would be true. Now, we want to make the second premise true. We're going to make it true by saying that maybe A is not Q, and then we can just make the first premise true by letting B have the property Q. So now it's true that something is either P or Q because B has Q. It is true that something is not Q because A is not Q, but it is false that something is P because in this interpretation, nothing is P. All right, next problem is asking you to do something a little bit different. It's asking you to show validity by thinking about interpretations. I don't want something very sophisticated as answer to this problem, just a cogent argument that explains why there can't be an interpretation that makes this premise true, but the conclusion false. So why is that? Suppose there was such an interpretation. What would it be for the premise to be true? Think about what the columns for P and Q would look like. Say that there is an object O, whatever object this might be, that has property P. Then this object must also have property Q, because if it didn't have property Q, then for all x, if Px, then Qx would be false, right? But if it's always the case that whenever something has P, it also has to have Q, then there can't be an object that has P but lacks Q. Right? So this no interpretation that makes the premise true can actually allow the existence of an object that makes P true but Q false. It might be even useful here to visualize what's happening with Venn diagrams. So suppose that you have a domain of object which will represent as a rectangle. You have P being the smaller set of objects, and you have Q being the larger set of objects. Now, everything that has property P also has property Q. And if that's the case, there just can't be an object that has P but lacks Q, because P needs to always be drawn inside of Q. Okay. Now, problem 7 is a little bit trickier, and here's one way of thinking about it. In problem 7, premise 1 says that there is an object, O, that has F or G, but we don't know which one it has, as one of those two. So it could be either that it has F or G. We'll try both cases. Suppose that it has F, then by the second premise says everything that has F has G and vice versa. So for every x, f of x, if and only if g of x. So then it has to have g. And so then it follows that there is an object that is both f and g. Now, take the other approach instead and say, well, what if the first premise was made true by an object that has g? Well, then, by the second premise, that object also has to have f. And again, we are in a situation that makes the conclusion true. So whenever these two premises are true, the conclusion must be true. When you answer these questions like this in the final, I don't want you to give anything mathematically sophisticated or even all that precise. I'm just seeking some clarity of thought, understanding what the task of showing validity would be, and pointing out the relevant facts that would suffice to establish validity. Okay, now the next one doesn't tell you whether the argument is valid or invalid. And the way I suggest you approach this one is just by trying to come up with an interpretation that makes the premises true and the conclusion false. And if you succeed, that means that the argument is invalid. And if you find trouble, that means that the argument is valid. So what would be an interpretation that makes the premises true and the conclusion false? Let's start again from let's first start by having a domain. We're going to choose two objects as our domain, A and B. Let's start by the forced facts. If nothing is F, we need to have minuses here. Okay. Now it's going to follow that nothing is F and G automatically, because if nothing is F, then nothing is F and G. So this first premise is true as well, just because we made nothing F. But now we could make G a plus. And so here now it would be true that nothing is both F and G, so that premise would be okay. It would be true that nothing is F, but it would not be true that nothing is G because something is G. All right, that's the last of the interpretation problems. Let's move on to the formal proofs. The next problem asks you to fill in a formal proof that's already begun. So how are we going to fill this in? I think the most natural place to look is sort of trying to understand what's going on here towards the end of the proof, right? Clearly what's happening is that we are trying to use a universal introduction in the last step. We're going from something that doesn't have a universal in line 8 to something that has a universal in line 9, and it seems like that step is a universal introduction step. If it is a universal introduction step, which we have every reason to suppose it is, then we know what's going to go in this box, because the only thing that can go in that box is QA. Because for you to do universal introduction here, you would have to replace the name with a variable and attach a universal quantifier. Okay. Now this next up, this box, this is pretty easy because this is said to be indirect proof. Indirect proof needs a subproof in which you assume something and derive a contradiction. There is only one subproof here this could be, which is the subproof that goes from 3 to 6. Now, if this is a correct application of indirect proof, this one needs to be contradiction. Now, what about this box here? Well, this box is the last line of a conditional introduction. And so if the conditional has PA as antecedent, in that box, we got to put the consequent of the conditional, so we're going to have to put QA as well, given what we derived. Okay, now let's move on to this box here. What could go in that box? So what's happening here is that we're doing a proof by negation elimination in this step, because that's the typical way in which we derive contradiction symbols. And basically what we're doing is we're taking line 1, and matching it with a proof of the thing inside the negation in line 1. So we already know that this box here is going to be EY, PY, and not QY. Okay, which makes sense because this is also said to be an existential introduction, presumably from the previous line. And all that we have to do to make it an existential introduction from the previous line is make sure that that is conjunction. And to make sure that that's conjunction, the only thing that we have to do is say that this is conjunction introduction. All right, so I think if you think through this proof, all of these boxes are pretty much required as long as you know what the rules are of the formal system. All right, problem 10 tells you to construct a proof of it's not the case that there is a y py and not qy from the premise for all x, if p of x, then q of x. Okay, now in doing this proof, we follow the very same thing that we always follow. We're gonna look at our main connective of our goal. We're gonna try to use the introduction rule of the main connective. In this case, that means it's a negation. So it means we assume the thing inside the negation. And we try to prove a contradiction. And if we succeed in proving contradiction, we are done. Now, the basic strategy I've given you for proving contradiction was to look for something negated and prove the thing inside the negation. But right now, we don't have something negated among our available materials. So we have to do some work. The most natural thing to do would be to try to eliminate this existential quantifier. What we will want to do is say we're going to give a name to that object that has P but does not have Q. We're going to call that object O, just like we did in class today. And remember, in an existential elimination, the goal inside the existential elimination subproof is the same as the goal of the existential elimination. Now we can eliminate the universal in premise 1. We say if PO, then QO. 5, we get PO from 3 by conjunction elimination. So let me just say this one is for all elimination from line 1. 5 is conjunction elimination from line 3. We're going to need some space here for one more line. I'm going to delete these. I'm trying to write a bit smaller. So we're going to use PO and this conditional to derive QO. So this is going to be conditional elimination based on lines 4 and 5. Line 7 is going to be negation elimination. Oh, based on lines that we don't have yet. All right, I got to do this proof in a way that where I have more space. I'm going to do it all again. It's going to be the same proof. I'm just going to write it here. Slightly more, slightly greater length. So my premise was for all x, px, conditional qx. My conclusion is it's not the case that there is a y, py, and not qy. I'm going to start a subproof in which I assume ey, py, and not qy. And my goal in this subproof is to prove contradiction. But what I said earlier is I couldn't just prove contradiction in the way that we're familiar with. I needed to do an existential elimination. So I'm going to assume PO and not QO, and I'm going to try to get contradiction inside that same subproof. I'm just repeating the same steps I did on the left here. I'm going to eliminate the universal quantifier in line 1 with O. So I say that this is for all elim based on line 1. Step 5, I eliminate the conjunction. I get PO. So this is conjunction elimination based on line 3. Step 6, I get QO. So this is conditional elimination based on lines 4 and 5. 7, I now get not QO by doing conjunction elimination based on 3. And now I've got QO and I've got not QO, and that's a contradiction. So I can say I'm going to do negation elimination based on 6 and 7. And now I've completed my existential elimination, and I can say Okay, I had an existential in line 2. And in line 3, I started an existential subproof, which I ended in line 8. And the goal of that subproof was contradiction, so contradiction follows. Lastly, we have a negation introduction based on the entire subproof from 2 to 9. So that's that proof. Let's look at it a little more carefully. Okay, now I'm gonna solve the last problem, which was this, to give a formal proof of this argument. I gave a hint for this problem, which is on the last page of the final. Right now, I'm gonna solve this with the hint in mind, but without checking the hint. If you wanna follow along with the hint, I just recommend that you just look at the paper where I have the final and just follow along with the steps. So premise 1 is for all x, for all y, rxy, conditional ryx. This basically says that r goes both ways. If it goes from x to y, then it has to go back from y to x. Premise 2 is that r relates z to b, and the conclusion is that r must relate b to z. And so the idea here is going to be this. This is also what I suggested in the hint. We're going to start an existential elimination. I'm going to say, well, call this object O. Whatever object Z that we're talking about, call it O. That's an assumption. What we want to prove is that, actually our final goal, we're just going to prove that there is a Z RBZ. Because remember, in existential elimination, your goal inside the subproof is always the same as your goal outside the subproof. But in particular, we want to prove this thing. We want to prove this by proving RBO. Because that's the object that we really care about right now. So now this proof has become quite simpler. We're just trying to go from ROB to RBO in a context in which we know that for every x and for every y, if rxy, then ryx. So we just have to make sure that we eliminate these universal quantifiers in such a way that we use the right names. So here's how we're going to do it. First elimination, we're going to say for all y, r o y conditional r y o. So this is saying for all y, if y relates to Olga, for all y, if Olga relates to y, then y relates to Olga. And it's a consequent of line 1 by universal elimination. Next, we're going to also eliminate the second universal quantifier. This is the same thing that we did in class today. We had 2 universal quantifiers, and we eliminate them one by one. And then here we do ROB conditional RBO by another universal elimination based on 4. Okay, and now we just get to this thing that we needed by conditional elimination based on lines 3 and 5. This step 7 is an existential introduction based on line 6. And step 8 is an existential elimination, which started with the existential claim on line 2 and then was developed in a subproof that started in line 3 and ended in line 7. All right, so that's the proof of this other problem following the strategy that I have outlined in the hint. That's also the last problem in the practice final. So I hope these are the answers that you guys also got for your own problems.